Okay, so let's start the recording for today. We last left off on handling exponents and powers of 10. Now, why did we go over handling exponents and powers of 10? Well, scientific notation, which is our way of expressing large and very, very small numbers, is fundamentally based on powers of 10. Scientific notation is of the form a number times 10 to the n. And remember, the number that we use for scientific notation must be less than 10 and greater than or equal to 1. Okay? So then, if we try to write a number in scientific notation, here's the step-by-step process. So let's suppose we're looking at the number 5,437. Okay? So our first order of business, we write our number and then we place a decimal point at the end. So I'm going to place my decimal point at the end. Okay? Now, our next step is to move the decimal point until the number is greater than or equal to 1 and less than 10. So if we have 5,437, let's do a little bit of a test. So if I move my decimal point over one time to the left, do I have a number between 1 and 10? Is 543 between 1 and 10? No. So let's try one more time. Okay. What about 54.3? Is that between 1 and 10? I see a lot of no's in the chat. Let's try one more time. Is 5.437 between 1 and 10? Yes, so we put a check mark. Now, what we do is we count how many places the decimal point was moved, and if it was moved to the left or to the right, the direction matters. If we moved our decimal point to the left, n is equal to the number of spaces moved to the left, and n is positive, okay? So in this case, we have 1, 2, 3, so n is equal to 3. So we'd write out our number as, so 5,437 is equivalent to 5.437 times 10 to the n. And what did we just say the value of n was? What did we say n was equal to? 3. N is positive when we have large numbers. Let's look at another example where n is negative. So if we have 0.0347, okay? So let's move our decimal point. So this time I'm moving it one space to the right. Do I have a number between 1 and 10? If I move it one space? No. So let's try one more time. I move it a second space to the right. Okay. Now, looking at 3.47, do I have a number between 1 and 10? Yes, most definitely. Okay. Now I count the number of spaces I moved my decimal point to the right. 1, 2. So this would be our value of n. If we move our decimal point to the right, n is equal to -1 times the number of spaces to the right. So in this case, instead of +2, n would be equal to -2. Okay, so we have 3.47 times 10 to the -2. Small numbers have negative powers of 10 in scientific notation. Does this make sense to everyone? Any questions on this idea? Okay, so let's keep going now. And let's do some examples. I'll do the first two, you'll do the second two. So we're asked to convert the following numbers to scientific notation. So we have 4,534. I don't like my commas to ever be present in my number, so I'm going to get rid of the comma. I'm going to put a decimal point at the end. Now I'm going to move my decimal point 1, 2, 3 spaces. So I'm moving 3 spaces to the left. And that in turn gives me a number of 4.534. And we know my n is equal to 3, so we write it as 10 to the third. Looking at this other number, we have 0.00342201. And that may seem like a lengthy number, but you do have to keep all of the digits. When you're writing numbers in scientific notation, do not get rid of any of the digits. So now to get a number between 1 and 10, I'm going to move my decimal point a total of 1, 2, 3 spaces, except this time I'm moving my decimal point 3 spaces to the right. That in turn gives me 3.4201, and this time instead of a positive exponent, we have a negative exponent. Large numbers, positive exponent in scientific notation. Small numbers, negative exponent in scientific notation. Do these two examples make sense to everyone? Any questions? Notice how I wrote out the full number. Oh, the decimal always goes at the end for large numbers. The leading zeros you can get rid of, but anything at the end of your number, you have to keep. Does that make sense? Okay, so let's work on the following examples. So I'd like you to look at the following two numbers, and I'd like you to try to convert the following numbers into scientific notation. Allow me 1 second. There's a small delay in OneNote. So let's spend about 3 to 4 minutes, and let's try to convert the following numbers into scientific notation. And don't be shy to share your responses in the chat or unmute and share your responses verbally. You can also ask a question via the chat or verbally. Let's try to get a few responses in the next 3 to 4 minutes. This is going to be a common activity that we do in lecture where we take a pause and we work through problems. And I highly encourage you to use the chat or unmute and share your responses verbally. Or you can use the annotate feature, which is a little pen icon in your Zoom overlay, if you'd like to draw out your proposed answer.
First one is 3.7 times 10 to the negative 2.
Yep, exactly right. I see a lot of responses for the first question. So if we have 0.037, we move our decimal point a total of 2 spaces to the right, and that in turn gives us 3.7 times 10 to the negative second. Wonderful. Thank you for sharing, and I also greatly appreciate that everyone is sharing in the chat. One thing I always want everyone to note, when we move our decimal point to the right, our exponent is negative. If we have a small number, we have a negative exponent. So let's take another few minutes, about another 2 minutes, and let's work on this second example. And don't be shy to share your responses in the chat. And wonderfully, we see at least 5 responses in the chat. So to walk us through the logic for this problem, we have 15.607. We need to move our decimal point 1 space to the left. So that in turn gives us 1.5607 times 10 to the first. We have a large number, so we have a positive exponent. Do these two examples make sense to everyone?
Oh, question.
Yes. Mhm.
So do we need to write 10 to the first? Can we just omit the first? Just 1.567 times 10, not like 10 to the first?
So in scientific notation, you typically include the power of 10 just for completeness. So the 10 to the first, it's better to include that it's 10 to the first, so that way it's unambiguous and it's as clear as possible. That it's written in scientific notation rather than a mathematical operation. But if you write times 10 on an exam, I'd still accept it. Does that make sense? Perfect. Any other questions on these examples that I can address? Okay, so let's keep going now. And this time we're going to go in reverse. We're going to convert the following numbers in scientific notation to a decimal. Okay, so let's recall, and I'll do these two examples to help us recall how to handle multiplying and dividing by exponents. And just as a reminder for students who have received a Zoom invite today, I also sent you a copy of the notes in my email. So continuing on, when we're multiplying or dividing by powers of 10, so in this case, we're multiplying by 10 to the positive fourth. When we multiply by a positive power of 10, this is telling us that we move our decimal 4 spaces to the right. So let's show how this works in practice. So we have 3.70. We're multiplying by 10 to the positive fourth. So we move it 1, 2, 3, 4 spaces to the right. That in turn gives us 37000 or 37,000. One nice way to check your work is you can count the total number of digits past your decimal point, and that allows you to check that you've moved your decimal point correctly. Does this look familiar from Monday's lecture? Okay. So continuing on, let's look at this second example where we're asked to multiply by a negative power of 10. So we have 0.105 times 10 to the negative second. And this negative power of 10 is telling us that we move our decimal, in this case, 2 spaces, this time to the left. Okay, so let's process that. So we have 0.105. Okay, and now what we're going to do is we're going to take our decimal, we're going to move it 1, 2 spaces to the left. That in turn gives us 0.00105. It is traditional that you place a 0 in front of the decimal point, just to be completely clear about the location of the decimal point. Does this example make sense to everyone? So now that we've seen some representative examples, let's take a moment and let's try to convert the following numbers to a decimal. So let's look at examples A and B. Let's take about 4 minutes to work on these two examples. And don't be shy to share your responses in the chat or to unmute and share your responses verbally. And I'm already seeing some reasonable responses in the chat. Let's spend another few minutes and let's try to get a few more responses. And for those working on this problem, don't worry if you take a little bit of time to get a response. That's more than okay. This may be the first time many of us are seeing this content, so it's always important to be methodical, and as long as you're working through it step by step, you'll reach the correct answer. And the responses I'm seeing in the chat look great so far, and we'll discuss example A in about another minute. And it's wonderful to see the class participating in this way. And if there are any questions that I can answer in the chat or verbally, don't be shy to ask a question. So let's look at this first example, and I'm going to show you two methods. The first is the method that we've seen very commonly. A second method is known as the addition method. So first and foremost, we have 0.00435 times 10 to the 6th. Okay, so this 10 to the 6th is telling us that we move our decimal 6 spaces to the right. Okay. So that in turn gives us, we have 0.00435. So we move our decimal point 1, 2, 3, 4, 5, 6. And we place a 0 at the end as a placeholder. That in turn gives us 4,350. Okay, so that's one method. The other method that you'll commonly see in your textbook is known as the power of 10 method or the addition method. So I'm going to rewrite this 0.0435 as 4.35 times 10 to the negative third. Now when we multiply it by 10 to the 6th, here's a really important trick. When you multiply powers of 10 together, what you can do, and this is why powers of 10 are so wonderful, you can take your two powers of 10 and add them together. So that in turn gives us 4.35 times 10 to the third. And then I can process that as normal. So I move my decimal point 1, 2, 3 spaces. And that gives me 4,350. The reason why I'm showing you this addition method is this thought process will come up a lot when we start dealing with unit conversions. Both methods are fine. I'm just showing you a mix of methods so you can pick which one you prefer. Let's take a few more minutes and let's take about another minute to a minute and a half and let's continue working on this second example. This time we're dividing by a positive power of 10. Let's try to get a few more responses in the chat and then we'll discuss example B in about another minute. And if you have any questions so far, don't be shy to ask them in the chat or verbally. I see quite a broad array of responses. So let's now look at question B. So we have 20 point, we have, whoops, I'm getting ahead of myself here. We have 20,190 and we're multiplying by 1 over 10 to the third. Now we can rewrite this 1 over 10 to the third as 20,190 times 10 to the negative third. Okay, so now we have our clear instructions. We need to move our decimal point 3 spaces to the left. Okay, so if we have 20,190, we place our decimal point at the end, and then we move our decimal point 1, 2, 3 spaces to the left. That in turn gives us 20.190. Keep in mind that the base number that we're multiplying by our power of 10 is 20,000. So as a result, when we move our decimal point 3 spaces to the left, we end up with an end result of 20.190.
So what about the 20.19? Is that the correct answer?
Yes, that's actually, and that's a great segue. If you're dealing with this number in the lab, you'd actually report your final answer as 20.19. And the reason for that has to do with the fact that this 0 is what we call insignificant. It's not a significant figure the way this number is written. And we'll talk more about significant figures actually later in the lecture. So 20.9 is actually a more correct response for this problem. But in order to have the necessary information to explain why that is, we'll need to talk about a few more topics. But that's a really good question. Thank you for bringing that up. Any other questions that I can address? So let's keep going now, and let's talk about units of measurement. So units really serve to provide meaning to numbers. The units indicate what quantity, what you are actually measuring in our world, and what standard unit of measurement you are using. So for example, a measurement has a number, for example, 10, and then a unit of meters. Now, in science, so in the US, we happen to use the English system, but the majority of the world and in scientific discourse, we use the metric system. Now, for those who are wondering, I always try to find a major specific example of how units can really play an important role in our day-to-day lives. And I just want to talk about a nice little case study, especially for those who are going into nursing. So in this story, a 17-month-old toddler was brought in with concerns about an eye infection. They took a lot of the patient's vital signs, including their weight. They diagnosed the patient and prescribed them a dosage of a common antibiotic. Now, the one thing that I found really quite interesting about this case study is that the paperwork listed a weight of 25 kilograms rather than the true weight of 25 pounds. Now you may say, is that a huge difference? Well, if we compare a kilogram to a pound, if we compare a kilogram to a pound, 25 pounds is roughly 11.3 kilograms. So the listed weight was almost double the patient's actual weight. Now, why is this an issue? Because the weight was entered incorrectly, that changed the dosage. And this resulted in the patient receiving an excessive dose of the antibiotic. Thankfully, the patient was unharmed in this process, but even a subtle difference in the unit noted for a patient's weight can make a huge difference in dosing and patient outcomes. So this is a nursing relevant example for why units matter and why accurately recording units is incredibly important. I always like to share stories like this when I see them in the literature. So let's talk about unit conversions. Let's try to look at how we can equate different units of measurement. Now, the metric system is really wonderful because it's based on powers of 10, making scientific notation especially useful. The metric system is based on what are known as base units. So the common base units for distance, we have units of meters. For mass, we have units of grams. Volume, the base unit is liters. Time is seconds. And temperature is Kelvin. Now, for those who grew up using the metric system, you may say we commonly take our temperatures in Celsius. So yes, Celsius is also included in the metric system, but Kelvin is far more important in science and in chemistry. So these are the base units that you should be familiar with. And these are standard units of measurement that correspond to a discrete quantity in our physical world. So the meter is a discrete distance in our physical world. Okay, now to indicate large or small quantities of a unit of measurement, the metric system utilizes a set of common prefixes, each with a unique symbol. Now the prefix modifies our base unit. The prefix modifies our base unit in order to generate what is known as a prefix unit. So let's show an example of this process. So for example, a centimeter, we have a prefix modifying our base unit to give a prefix unit. Now, looking at each of our different metric prefixes, each of our prefix symbols corresponds to a power of 10. So each of these prefixes are representing a power of 10 amount of our base unit. So I have a list of all of the metric prefixes that I'd like you to memorize and be familiar with. And now we'll talk about how we can use these prefix units to modify our base unit. And this is really cool. If you want to convert a prefix unit to the base unit, all you do is replace the prefix with the power of 10. So let's do an example of this. 657 millimeters. Does everyone see this M prefix? This M prefix corresponds to milli. And what power of 10 does the milli prefix correspond to? What power of 10 do we see in our table?
-3?
Yep, exactly right. So we write 10 to the -3 in the place of our milli prefix. Now, all we do is we multiply our number by this power of 10, and that gives us 0.657 meters. So we've gone from a prefix unit to our base unit. Does that make sense to everyone? Let's do another example. So 457 kilograms. This K corresponds to the kilo prefix. So what power of 10 do I plug in? What power of 10 corresponds to kilo?
+3.
Yep, exactly right. So this 10 to the +3 is replacing our kilo prefix. That in turn gives us 457, and we move our decimal point 1, 2, 3 spaces to the right, and that gives us 457,000 grams. So prefix to base unit conversions are really straightforward in the metric system. All you do is you replace your prefix with its corresponding power of 10. Any questions on this idea? Any questions on these metric prefixes. The prefix represents a large or small amount of our base unit.
So basically we have to memorize this chart here so we can know how to convert it.
Yes, you need to be familiar with the common metric prefixes, as they come up a lot in unit conversions in both later chapters of this course and in the laboratory section of this course. So let's keep going now, and let's talk about unit conversions and how they actually function. So, as we can see from this figure, different units and numbers can describe the same quantity, right? Centimeters and inches both describe distance. And we know that 2.54 centimeters is equal to 1 inch. Does everyone notice how if we look at these two lengths, 2.54 centimeters is the same length as 1 inch? Does everyone see how they represent the same length in our physical world? Now this is important because if we have two numbers and units that are describing the same quantity, the same distance in our physical world, we can create what is known as a unit conversion. And a unit conversion is a ratio of two equal quantities. So if we know 2.54 centimeters are equal to 1 inch, we can write out a ratio where we have 2.54 centimeters per every 1 inch, or we have 1 inch for every 2.54 centimeters. Unit conversion factors are a ratio of two equal quantities. Two quantities that are representing the same value in our physical space. Now, why is this useful? Well, we can multiply any quantity by 1 and that quantity is unchanged, right? If I said 2 times 1, that's obviously going to be 2, right? In unit conversions, you are multiplying your quantity by 1. However, the trick in unit conversions is that your units and number will change when you perform a unit conversion. The value, what that unit and number represents in our physical world does not change. Okay. So when multiplying and dividing by unit conversion factors, the units will cancel just like normal numbers, right? So if we have 7 times 2 over 7, we can cancel the 7 on top and the 7 on bottom, right? Because we know that 7 divided by 7 gives us 1, right? Likewise, if we wanted to convert from centimeters to inches, we take 2 inches and we multiply it by our conversion factor. Remember, this conversion factor is just equivalent to 1. Think of it like we're just multiplying by 1. Now, since we have inches over inches, the inches can cancel because inches over inches, a quantity divided by itself is equal to 1. So in the end of our unit conversion, we end up with a new number and a new unit. Does this make sense to everyone? So write out your units and you'll see very clearly that if you have a unit on the top and on the bottom that's the same unit, it will cancel. Don't worry, we'll do more practice on this. I'm just explaining to you why these unit conversions actually work. Now, one thing that you do need to be aware of is you need to make sure that the units cancel and that you write out all of your units. So for example, 5 centimeters squared, we have a complex squared unit is equivalent to 5 centimeters times centimeters. Likewise, a centimeter cubed is equal to 1 centimeter times centimeter times centimeter. it's really important that you write out all of your units in order for you to effectively perform a unit conversion. You need to convert all of the units. Any questions on this section? So you want to cancel out all of your starting units so that you're left with your desired units. And we'll talk about that actually on the next page. So let's go through a step-by-step guide. So how do you convert from one unit of measurement to another unit of measurement? So to start us off, we're going to try to answer the question, how many milligrams are in 3.46 times 10 to the first kilograms? So first things first, we have to indicate what units that we're starting from. So what are starting units? What are the units associated with the number that we're given? What are we starting out with? So we're asked how many milligrams are in 3.46 times 10 to the first kilograms. And your starting units are almost always associated with the number that you're given. So we're starting off with 3.46 times 10 to the first kilograms. So kilograms are our starting units, okay? So we're starting off from kilograms, and let's ask the question, what units are we trying to convert to? What is our end goal? Our end goal is milligrams, okay? Now, I don't like going directly from prefix to prefix. That often creates problems. So instead of going directly from prefix to prefix, instead, what we're going to do is we're going to go through the base unit. So what is our base unit? What is the base unit shared between kilograms and milligrams? What's the base unit? Grams, okay? So we're going to go from kilograms to grams to milligrams. This is what I like to call a solution map or a unit conversion map. We'll be using these a lot in the first half of this class. Okay, so now what we're going to do is we're going to identify a conversion factor containing the desired base unit and the starting prefix unit. Okay? So if we have 3.46 times 10 to the first kilogram, and we want to go from kilogram to gram, okay? Let's try to answer the question. In 1 kilogram, that's equivalent to how many grams? What does the kilo prefix correspond to?
1,000.
Yep, 1,000 or 10 to the third. I like writing things in terms of powers of 10, though you're more than welcome to write it as 1,000. I just find when you write it in terms of powers of 10, it's easier for you to add and subtract the powers of 10 when you're performing your unit conversion. But yes, that's exactly right. Okay. Now, when we're going from kilogram to gram, I draw this little arrow and I put where I'm trying to go, where my arrow is pointing, I put it on top. So what units am I going to put on top of my unit conversion factor? If I'm trying to go to grams, I put grams on top. And the grams has this 10 to the third associated with it. In general, you're always going to have your power of 10 with your base unit. Now, if I'm going from kilograms, what is going to go on the bottom? If I want to get rid of kilograms, what goes on the bottom?
Kilograms.
Yep, exactly right. So in general, when you're setting up your unit conversion factor, you put what you want on top and you put what you're starting out with on the bottom. So now that we have our conversion factor, we're going to convert from our starting prefix unit to the base unit. So we have 3.46 times 10 to the first kilograms. And we know that we have 10 to the third grams per every 1 kilogram. As we can see very clearly, kilograms are on top and bottom, so we can cancel them. And that in turn gives us 3.46 times 10 to the first times 10 to the third gram. And remember, as we discussed, if we have powers of 10 that we're multiplying together, we can add our powers of 10. So 1 plus 3 gives us 10 to the fourth. So we end up with 3.46 times 10 to the fourth gram. Does this first step make sense to everyone? Does this make sense to everyone? Any questions on this first step? So in summary, you write out your starting and desired units. You indicate and you generate an equality relating your prefix unit and your base unit. You then write a ratio containing what you want over your starting unit. Then you multiply your number by the conversion factor and you add the powers of 10 together. Okay, so let's keep going now. We're actually not done with this problem. So we have 3.46 times 10 to the fourth grams. And when we look at our solution map, we want to go from kilogram to gram to milligram. So we've checked off our first step. Now, we did our first step. We went from kilograms to grams. What else do we still have to do? What do we have to do next? We have to go from grams to what unit? What unit are we trying to get to now? Milligrams, okay? So my question to all of you is 1 milligram is equal to how many grams? What does the milli prefix correspond to?
10 to the negative 3.
Yep, exactly right. 10 to the negative third, that's perfectly correct. So now that we have our ratio, now that we have our equality, we need to generate our unit conversion factor. Now, because we're trying to go to milligrams, what units go on top? What units go on top? Milligrams, exactly right. So we have 1 milligram. And what unit are we trying to cancel? What unit goes on the bottom? Grams. But that grams has a power of 10 associated with it. We have 10 to the negative third gram per milligram. Perfect. So now that we have our conversion factor, we have what we want on top and what we're going from on the bottom. Now all we have to do is multiply by our conversion factor. So let's do that on step 8. So we have 3.46 times 10 to the fourth grams. And we know that we have 1 milligram for every 10 to the negative third gram. Okay, grams cancel, and we're left with 3.46 times 10 to the fourth times 1 over 10 to the negative third milligrams. Now, to help everyone out with the power of 10 addition, if we have 10 to the fourth times 1 over 10 to the negative third, that's equivalent to 10 to the fourth times 10 to the third. We add our powers of 10 together. That gives us 10 to the seventh. So our end result is 3.46 times 10 to the seventh milligrams. Now, as you get more experienced with these unit conversions, I would highly recommend trying to do these unit conversions in one line. So let me show you an example of a one-line conversion. So if we have 3.46 times 10 to the first kilograms, we know that we have 10 to the third gram per kilogram. Kilograms cancel. We also know in 1 milligram, we have 10 to the negative third gram. Grams cancel, and that gives us 3.46 times 10 to the 7th milligrams. So these are two potential methods for solving these unit conversion problems. As you progress through this class, you're going to eventually start to use these one-line conversions more and more frequently. Does this make sense to everyone? Now, you really need to always go through the base unit. It's best not to try to skip steps in these unit conversions because that's often where students make mistakes. It's easier to check your work if you write out your units clearly and you clearly show each step of your thought process. So this can help you organize your thoughts so then you can start to develop efficiency in solving these problems. Any questions on these examples? Any questions? If not, let's try to draw out some additional questions, and I'll work through another example for everyone's reference. So we're asked how many nanometers are in 4.5 times 10 to the fourth picometers, okay? So first things first, my starting units are picometers, and my ending units are nanometers. Remember, your starting units are overwhelmingly going to be associated with your number that you're given. Okay? However, I'm not going to go directly from picometer to nanometer. Instead, what I'm going to go is I'm going to go through the base unit of meters. Okay? Now that I have my solution map, we're ready to begin. So in the first step, I'm going to go from picometer to meter. So if I have 4.5 times 10 to the fourth picometer, I know that 1 picometer is equal to how many meters? I'm going to need everyone's help here. What does the pico prefix correspond to? It's
10
on-
to negative 12.
Yep, exactly right. 10 to the negative 12th meters. Picometers, I like to think of as the atomic scale. Many bond lengths and atomic radii, the size of atoms, are measured in picometers. Okay, so now that we have our equality, what we're going to do is we're going to generate a unit conversion factor. So if we're going to meters, what units need to be on top?
Meters.
Yep, exactly right. So we have 10 to the negative 12 meters, and we're going from picometers, so we put picometers on the bottom. Picometers cancel. And for our first step, that gives us 4.5 times 10 to the negative 8 meters. Okay, now we're trying to go from meters to nanometers. So we have 4.5 times 10 to the negative 8 meters. And let's set up a new equality. So 1 nanometer corresponds to how many meters?
10 to negative 9.
Yep, exactly right. Okay, so now that we have this ratio established, if we're going 2 nanometers, what units go on top? What units do we need on top? If we're going 2
Nanometers.
Yep, so we'd want nanometers on top. So 1 nanometer, and then we're going from meters, so we put our meters on the bottom. So we have 10 to the negative 9th meters on the bottom. So then that gives us 4.5 times 10 to the first nanometers. And just to showcase how that works, when we have 10 to the negative 8th times 1 over 10 to the negative 9th, that's equivalent to 10 to the negative 8th times 10 to the 9th, and that gives us 10 to the first. Does this make sense to everyone? Does this logic of unit conversions make sense? You draw your arrow, you put the unit that you're going to on top, the unit that you're going from on the bottom. And remember, the power of 10 always goes with the base unit. That's why this method is nice, because it's very consistent. So, with that established, I'm going to do one more example. This time I'm going to show you a one-line method. So in this case, we're asked how many centimeters are in 0.5 times 10 to the negative third millimeters. So I'm starting off with 0.5 times 10 to the negative third millimeters, and I want to get to centimeters. So what base unit am I going to go through? What base unit am I going to go through? Meters, exactly right, exactly right. Okay, so now that we have this set up, I'm gonna write some equalities. So 1 millimeter corresponds to how many meters? What does the milli prefix correspond to?
10 to the third. Oh, 10 to the negative third.
Yep, exactly right. The milli prefix corresponds to 10 to the negative third. Okay, I'm also going to write for my reference the centi prefix. So 1 centimeter corresponds to how many meters?
10 to the negative 2.
Yep, 10 to the negative second. That's exactly right. Okay, so now that we have our equalities, I'm going to write out my base number, and in the one-line method, I'm going to set up each of my conversion factors, each of my unit conversion ratios, one after another. So first things first, I need to go from millimeters to meters. So what units are going to go on top? Meters, okay. And I know from my first equality that we have 10 to the negative third meters per every 1 millimeter. So let me keep the coloring consistent. Okay, millimeters cancel. And now for my second step, I'm going from meters to centimeters. So then, what units do I need on top?
Centimeters.
Yep, and in 1 centimeter, we have how many meters? 10 to the negative second. Okay, we put what we want on top, what we're starting from on the bottom. Meters cancel, and we're left with the following answer. So we have 0.5 times 10 to the negative third times 10 to the negative third times 1 over 10 to the negative second, which gives us 5 times 10 to the negative first times 10 to the negative third times 10 to the negative third times 10 to the second. And if I add up all my powers of 10, I in turn get 5 times 10 to the negative fifth centimeters. because we have -7 plus 2, which is -5. Does this example make sense to everyone so far? Any questions on this example?
Where did you get the -1 from?
Because if we're going from 0.5 is equivalent to 5 times 10 to the negative first. Does that make sense?
Yes, thank you.
And when you're handling a string of power of 10 multiplication operations, your calculator will actually be able to add up all these powers of 10 for you. I'm just showing you how to do this by hand, just so that way, rather than spending time entering things step by step in the calculator, you can instead quickly just add up the powers of 10. So you don't have to convert this 0.5 to 5 times 10 to the negative first. The reason why I did it is so that way I can report my final answer in scientific notation, which is a little bit cleaner than reporting my final answer as a decimal. So it's not required, it's just something that I do so that way my answer is as clean and straightforward as possible to interpret and to count sig figs for. And we'll talk about sig fig rules hopefully towards the end of today's session. So now that we've seen a few examples using both methods, what we're now going to do is we're going to work on a set of unit conversions. So we're going to start off and we're going to spend about 3 to 4 minutes, and we're going to try to determine how many microliters are in 153 milliliters. So let's spend about 3 to 4 minutes working on these examples. And I'd like you to submit your proposed responses in the chat or verbally. And if you have any questions working through this first example, don't be shy to ask. And the responses I see in the chat look good so far. Let's spend another 2 to 3 minutes on this example and then we'll discuss. Let's try to get a few more responses in the chat and then we'll discuss. I'm glad to see responses in the chat. I want to give everyone enough time to work through these examples, and then we'll discuss in about another 2 to 3 minutes. and we'll discuss in about another minute to a minute and a half as I see an array of responses in the chat. And just make sure that when you're performing your unit conversion, that you place the power of 10 with the base unit. So we see a nice array of responses. So let's discuss this example. So we're starting off with 153 milliliters, and we're trying to go to microliters. Okay. So what is our base unit? What base unit are we going to go through? Liters, okay? So now let's write out some equalities. So we know 1 milliliter corresponds to how many liters? What does the milli prefix correspond to? Ten to the
-3.
exactly right. 10 to the -3rd. Let's write out our second equality, 1 microliter. So this symbol is U for microliter. 1 microliter corresponds to how many liters?
10 to -6.
Yep, exactly right. 10 to the -6th. Okay, perfect. So in our first step, we're going from milliliter to liter. So if we have 153 milliliter, for our first unit conversion, we look and we find our equality containing milliliters and liters. And my question to all of you is, what unit goes on top in our first conversion? What are we trying to convert to?
Liter.
Yep, so we have 10 to the -3rd liter. And what are we going from? What units do we want to cancel? Milliliters, exactly right. So we have 10 to the -3rd liter per 1 milliliter. And as we see, milliliters cancel. For our next step, we need to go from liter to microliter. So then what units are going to go on top?
Microliter.
Yep, exactly right. So in 1 microliter, we have how many liters? 10 to the -6th, exactly right. Liters cancel. Okay. So now let's write out our powers of 10. So we have 153 times 10 to the -3rd times 1 over 10 to the -6th. And we can write this as 1.53 times 10 to the 2nd times 10 to the -3rd times 10 to the 6th. And if we add up our powers of 10, we get 1.53 times 10 to the 5th. And don't forget your units. These are microliters.
I have a question.
Yes.
What happened to the UL in the equation?
It sticks around. This is the micro. So the micro symbol when typed like this, but the micro symbol is written almost in cursive, and that's the kind of symbol that you'd see in your textbook.
Oh, okay, thank you.
So this is another way of writing the micro symbol. While the milli symbol is written explicitly like an M, while the micro symbol is a cursive U. Does that make sense?
Yeah. Thank you.
Perfect.
Professor, I have a question about the exponent.
Yes.
When we are typing on the keyboard, what symbol do we use for the exponent?
So for the exponent,
Uh-huh.
so so in Word, there's like a button, like where you see a superscript, and that's what you'd use for your exponent. If I can show you at the end of lab today in
Okay,
Word where to find that if you're typing it out. In Excel, you'd write it as number times 10, and then you'd enter the upper wedge symbol followed by your power.
Okay, thank you.
Mhm. And in the workbook, I actually have a tutorial on how to enter these numbers into your calculator as well. Okay, so the responses I saw in the chat were wonderful for this first problem. Let's do another example, and I'd like you to tell me how many milligrams are in 457 micrograms. So let's take about 3 to 4 minutes to work on this example. And then we'll discuss this example momentarily in about 3 to 4 minutes. And let's try to get some responses in the chat and any questions that you have in the chat. Let's try to get a few more responses in the chat and then we'll discuss. And if you have any questions at all, don't hesitate to ask them in the chat or verbally. I'm really pleased how this class is participating heavily in the chat and verbally, as it really helps me get a sense of how everyone's progressing through the material. And we'll discuss this example in about another 2 minutes. I want to give everyone enough time so that they can work through, double check their work, and if any questions arise, they can ask those questions. And the responses I'm seeing in the chat look really good so far, and we'll discuss in about another minute. Unit conversions are going to be the backbone of the first half of this class, so it's really important that we have this skill developed. Okay, so let's discuss this example. So in our starting unit, we're starting with 457 micrograms, and we're trying to go to milligrams. What is our base unit? What is our intermediate unit? Grams, okay. We also know that for 1 microgram, this 1 microgram corresponds to how many grams? 10 to the negative 6th, perfect. And 1 milligram corresponds to how many grams? 10 to the negative 3rd, perfect. Okay, so now that we have 457 micrograms, let's apply our first unit conversion. So we're going from microgram to gram. So my question is, how many grams are present in 1 microgram? Reading off, we see we have 10 to the negative 6th gram per microgram. Okay, for our second conversion, what unit is going to go on top? Milligrams or grams? What units are going to go on top in our second conversion? Milligrams, yep. Our arrow's pointing towards milligrams. We want milligrams in the end. Milligrams are on top. So we have 1 milligram for every 10 to the negative 3rd gram. Micrograms cancel, grams cancel, and that in turn gives us 457 times 10 to the negative 6th times 1 over 10 to the negative 3rd milligrams. And processing this further, that gives us 4.57 times 10 to the 2nd times 10 to the negative 6th times 10 to the 3rd. And that in turn gives us 4.57 times 10 to the negative 1st milligrams. And don't forget your units at the end. Does this make sense to everyone? Any questions on this example?
Professor, I actually have a question.
Yes.
How do you go from 457 to 4.57? Can you just explain that to me?
Yes, of course. So 457, we place our decimal at the end and moving our decimal 2 spaces to the left, that in turn gives us 4.57 times 10 to the n, where n is equal to 2. Does that make sense?
Yes, thank you.
Perfect. Any other questions on this example?
And just one more thing. And you just moved it 2 spaces to make it between 1 and 10?
Yes, exactly right. I always like to write my number in scientific notation because it makes many of the problems that you'll see in this class. I'll ask you to report your final answer in scientific notation. That and scientific notation makes it very easy to add and subtract your powers of 10. But if you're doing this in your calculator, you just enter this top string into your calculator and it will process all of the power of 10 issues for you. But I always like to show students how to do things by hand as a means of checking their work. Does that make sense?
Professor, I have a question.
Yes, please go ahead.
How do we know how to look at the unit conversion? Like when it's asking milligrams or in 457 UGs, like how do you, I don't know like what to look for.
Okay. So in general, your starting units will be the units associated with your given number. So notice how we're given 457 micrograms. So that's what we're starting out with. And when we're asked how many milligrams are in 457 micrograms, this milligrams is our target. That's what we're trying to figure out. Once we have our starting and ending unit, we figure out the base unit required to bridge these 2 units together.
Oh, okay. I guess my confusion on the UG, because on the unit conversion, it just has the U, correct? I was looking for U.
Yes. So the U is a prefix.
Okay.
And the prefixes can go in front of whatever base unit that we choose. And the prefix corresponds to a power of 10 amount of our base unit. So the prefixes are universal and they modify any of the base units that we use in the metric system. Does that make sense?
Yes.
So rather than looking for microgram together, when you're looking up the powers of 10, just look up the prefix.
The prefix. Okay, great. I was totally lost. Okay,
No problem.
thank you.
Mhm. Okay, so let's keep going now. And as this does come up in the allied health sectors, as in the US, we do happen to use English units, unfortunately. We're going to talk about English to metric conversions. Sorry, let me just check. So starting off, the 4.57 times 10 to the second is I'm just showing the student how I processed and wrote out my starting input of 457 in scientific notation. Once I have my number written in scientific notation, I added up my powers of 10 from my unit conversion expression. And so if we have -6 plus 2 plus 3, that gives me -1. That's where we get the 10 to the negative first from. When you multiply powers of 10, you can add the exponents together. Did that address your question? Perfect. So for English to metric conversions, you're not required to memorize the English to metric conversions. You'll have this sheet available. You can bring this English to metric and English to English conversion sheet with you to all exams. So you don't have to memorize any of these. So these are common English to metric conversions, and these are the common English to English conversions. So we'll reference this sheet throughout this next session. So English to metric conversions are handled exactly identically to metric conversions. The only thing that's a little bit tricky is that these conversions, their conversion factors aren't as clean. So let's look at an example. We're asked how many pints are in 20 quarts. So let's identify our starting unit. What are our starting units in this case? What are our starting units in this case?
Quarts?
Yep, exactly right. Okay, so we're starting with quarts, and what are our ending units? What are we trying to end up with? Pints, yep. Now, if we go to our English to metric or English to English conversions, we know, and this one's not in the table, so I'll provide it to you. We know that 1 pint is equal to 2 quarts. So just like before, now that we have our equality, we can use our equality to generate a conversion factor. So if we have 20 quarts and we want to go from quarts to pints, what units am I going to put on top? Pints, exactly. So we know in 1 pint, we have 2 quarts. Quarts cancel, and that in turn gives us 20 over 2, which is 10 pints. As you can see, it's not as fun doing English to English and English to metric conversions because the numbers are a lot messier. But the fundamental logic of writing an equality and writing out your unit conversion factor is exactly the same. Does this example make sense to everyone? So let's keep going now and let's do another example. So this one's a little more complicated. This is a multi-step conversion where we're asked how many milliliters are in 4 quarts. Okay, so we're starting off with quarts and we're trying somehow to get to milliliters. So now what we're going to do is we're going to go to our table. We're going to find as many conversion factors as possible in our table. So I'm going to go all the way up to my table and I'm going to look for something containing quarts and something related to milliliters. Is there an equality in this table that relates quarts and something related to milliliters? I see a lot of students typing liters. Yep, we have this relationship where 1.06 quarts is equal to 1 liter. The fact it's 1.06 is really frustrating because it could have been 1-to-1 and it would have just been a nice bridge. So we're going to take this equality and we're going to write this out. So here's what we know. Here's what we know. We know that we have 1.06 quarts equals 1 liter. This is what I like to call my bridge because it relates the English system to the metric system. And when you're doing English to metric conversions, you want to build your unit conversions around this bridging factor. So from quarts, we can go directly to liters, and we have that bridging conversion factor right here. Now we have a complete step-by-step conversion from quarts to liters to milliliters. Now what we have to do is we have to write out our equality. We know 1.06 quarts are equal to 1 liter, and we know that 1 milliliter is equal to how many liters? What does the milli prefix correspond to? 10 to the negative third. Perfect. So now that we have all of our equalities established, we're now ready to begin. So if we have 4.00 quarts, in our first step, we're going from quarts to liters. So what units go on top? What units go on top? Liters. So we know we have 1 liter, and what units are going to go on the bottom? Quarts. Yep. So we have 1 liter is equal to 1.06 quarts. Okay, so we bridged our first conversion. Next, from liter to milliliter, my question to all of you is, what unit goes on top? Milliliters. So we know in 1 milliliter, we have 10 to the negative third liter. Okay, so now if we punch this into our calculator, so we have 4.00 over 1.06 times 1,000, and that in turn gives us 3.77 times 10 to the third milliliters. We'll talk more about why I retained only 3 of the digits as my output. If you punch this into your calculator and you have it set to give you a raw number output, it should give you 3,770 milliliters. Does this example make sense to everyone?
Professor, how did you get the 3.77?
So I have my calculator set up so it gives me my output in scientific notation, but just to show you each of the steps, in this first output, we get an output of about 3.77. For our second operation, we have 1 over 10 to the negative third. We can write this alternatively as 3.77 times 10 to the third. Does that make sense?
No, I still don't get it, sorry.
So if we take 4 over 1.06 in our calculator, we get 3.77.
Okay, I get it.
And now that we're dividing by 10 to the negative third, we can write 1 over 10 to the negative third as 10 to the positive third.
Got it. Okay.
Does that make sense?
Yes, now it does. Thank you.
Perfect. And in lab, when I have my camera set up in a little bit of a different way, I'll be able to show you using my calculator how things are entered and processed. Yes, if you got 3,773, that's more than okay. We'll learn actually in the next page some of the rounding rules associated with reporting significant figures. Yeah. Any other questions on this example? Okay, so let's keep going now. And this is a workbook question. This is page 11, number 1. So if you're working through the homework, this is a good thing to pay attention to. So we're asked to perform the following conversion. 7,902 pounds. We're trying to convert pounds to ounces. So I'd like you to spend about 3 to 4 minutes working on this problem. And the first order of business is to go check our table of conversion factors. And I'd like you to tell me the relationship between pounds and ounces. And as I see in the chat, 1 pound is equal to 16 ounces. This is from the table, so you don't have to worry. Just to be clear that I'm going to write pound in red. So 1 pound is equal to 16 ounces. And you don't have to memorize that. That's just reading from the table. So given that conversion factor, I'd like you to convert from pounds to ounces. We're already seeing some reasonable responses in the chat. Let's give it about another 1.5 to 2 minutes to continue working through this problem and checking their work using their calculator. And we'll discuss momentarily. Let's try to get a few more responses in the chat before we discuss. As we see a large pool of responses, even though this looks somewhat more complicated, this is actually a one-step conversion. So we're starting off with 7,902 pounds, and we're trying to go from pounds to ounces. So then, what units do we need to place on top? What units are on top? If we're going 2 ounces, we need to put ounces on top. So we have 16 ounces per every 1 pound. Pounds cancel. So if we punch this into our calculator, 7,902 times 16, that gives us 126,432 ounces, and that would be option A. Wonderful, wonderful. So we're going to stop here for today as we're at the end of our scheduled lecture period.